Way to the side register. But yeah, and with some DVDs, take them.
Thank you.
Sure.
Good evening, everybody. Welcome to the February meeting of the Chester County Astronomical Society. Dave isn't here, so I will be filling in for him. As you can see, our guest speaker is already online, so without further ado, I'll turn the meeting over to Bruce there.
Yeah, we're gonna reverse our schedule a little bit because Marco's coming to us from Italy. It was 2:30 in the morning over there. So after the presentation, we do want to hand out for everyone who's here, who's getting one, which if you attended at least one event, one of our outreach events last year, you get a Night Sky Network pin, which honors the James Webb Space Telescope this year. So we'll do that after the presentation, but we're not going to ask Marco to stay up any later than necessary. Okay, so Bruce.
So, hi everyone. Thanks for coming out on Valentine's Day. I'm sure you heard a number of your significant others here, but they just need to realize what's more important. Right? So it's a real pleasure to introduce Dr. Marco Laveri tonight. Marco's a very renowned cosmologist and astrophysicist. He fairly recently accepted a position at the National Institute for Nuclear Physics in Genoa, hence the 2:30 in the morning call. And prior to that, he did postdoctoral work at Penn at the Center for Cosmology. And it was at that time, right around maybe February, March of 2020, that Marco actually talked to this group. And then we kind of had a hiatus for in-person meetings because of COVID. And prior to that work at Penn, he was also at the University of Chicago, the Calvin Institute for Cosmological Physics. So Marco received his PhD in astrophysics at the International School for Advanced Studies in Trieste, Italy. And I won't go into his research interests, but let's just say they're quite complex. Something you can really sink your teeth into, but one of the things that he has worked on is really models of expansion of the universe. And he's going to discuss that tonight, some of the limitations of those existing models, how we reconcile them, and what that information may tell us or shed new information about dark matter and dark energy. So, Marco, thank you again for doing this so late. We really appreciate it. Thank you.
Thank you, Bruce. Thank you for organizing this. Can you see my screen?
Yep,
Yes.
Looks good.
Okay, fantastic. Okay. I'm very happy. So as Bruce was saying, and Marco, it's really a pleasure to see you all. Yeah, and I really wanted to just remember when, before moving to the University of Genova as a junior faculty, I was a researcher in Penn, and that's where I first got in contact with Bruce and with you guys of CCAS, and I'm really happy that I got invited back for a talk, because my previous talk was my last in-person talk before the COVID pandemics hit, and lockdown hit. So it's fortunately enough, today we are having this talk over Zoom, not because of the pandemics, but because of normal life progression. So and I hope that the possibility of maintaining this type of Tuesday nights hangout type of contacts across continents is one of the silver lining aspects of the pandemics. So tonight I want to tell you about the latest development of my studies, and in particular the standard, something about the status of the standard cosmological model and the mysteries that the cosmology community is facing nowadays. So cosmological observations have become so precise that today we do have a standard cosmological model. This is based on several key components, including Big Bang theory, the concept of cosmic inflation, the presence of dark matter and dark energy, as you see here in the energy budget of the universe. And according to the standard model, the universe began in a hot, dense state about 14 billion years ago. and since then has expanded and cooled over time. And these aspects of the standard model have been measured to very high precision, but in a sort of Socratic way. We now know that we don't know much about our universe. Dark matter and dark energy, which make up the majority of the universe's total, matter and energy content, play a crucial role in its evolution, but are still of unknown physical origin. Right? So you see here basically the entire breakdown, that basically heavy elements, or what makes us, is basically less than 0.03%, and everything else is in stars and neutrinos, and that still makes below 1% of the entire energy budget of the universe. So since these, so the plan for tonight is to go through the physics and the description of the experiments that measure the expansion rate of the universe and the growth of cosmic structures, to highlight how these cornerstones of the standard cosmological model worked in this context, and to show you that today different ways of measuring these quantities are in somewhat disagreement between each other. And this leans into the possibility that the standard cosmological model might be close to a revolution that would possibly shed light on the nature of dark energy and dark matter, which are natural candidates for this type to solve this type of disagreements. So after discussing the status of these experiments, I'll show you some of the ideas that are floating around these days in the community. So the first one, the first point I want to discuss with you concerns the expansion of the universe. The discovery that the universe is expanding was a turning point in our understanding of the universe. So I'll go through it in some details, because then I want you to understand the problems we're facing today, and it all comes back to observations of distant galaxies. Edwin Hubble in the 20s, in the last century's 20s, by now, discovered that the Milky Way, our own galaxy, is not the only galaxy around. But if we look far enough, we see many more, right? So this is what you see here in this picture. This is one of the JWST deep fields, the JWST space telescope that recently became operative and made the headlines. And this field shows you a couple of stars and an abundance of galaxies. Most of the objects in these pictures are faraway galaxies that today are measured to exquisite precision and resolution. Now, when we observe these galaxies, and one of the key observations that Hubble made is that these galaxies are moving away from us. And we can tell that these galaxies are moving away from us because of Doppler effect. Can you hear me? Sorry, I've heard some noise. Please stop me if you have any questions at any point. Just raise hands, shout, and just try to interrupt me, so that I'll see it over Zoom. So we can tell that galaxies are moving away from us because of Doppler effect. That's basically what happens when we cross an ambulance on the other lane of the highway. And that's what you see portrayed here in the animation in this slide. When we have a wave source that's moving toward us, the crests of the wave get closer together because the source is moving, and we hear a higher pitch. Then the siren passes by, and the sound goes to lower pitch because now the source is moving away from us. So the wave crests are spread further apart. And the same thing happens for galaxies. We see the light emitted by chemical elements in other galaxies, but we don't see them as we see them in the lab, right? We see them with the exact same pattern, but at a different frequency, because the galaxy is moving away from us. And this phenomenon is called redshift, and it literally means shifting towards the red because sources are moving further away. Now, one of the key observations that led to the discovery of the expansion of the universe is that all galaxies are actually moving away from us. This was a realization from Hubble again, that all the sources that he was looking at were receding away. Now, as you can see in this animation, if we take a reference galaxy that we imagine to be ours, and we start stretching the picture, it would look like every galaxy was moving away to an observer in that reference galaxy. And not only that, right? From the perspective of a single observer, the further away the galaxy, the faster it would seem to move, right? When we stretch the picture. Now, if we fix our reference frame to another galaxy, as you're seeing in the animation, and stretch the picture again, the same would happen. The same stretching would look like all galaxies are moving away to any observer that sits on any galaxy in this animation. And these two observations, we see all the galaxies that are moving away from us. And this would exactly happen if we started stretching the universe, are what allows us to interpret the fact that the galaxies that we see are moving away from us. They don't hate us. The picture is stretching, right? The universe is expanding. So now, after we have realized that the universe is expanding, it makes sense to try to measure how fast it is expanding. And this was the third landmark discovery from Edwin Hubble, whose face you finally see in this slide here in the 30s. And he took measurements of distances and recession velocities of several galaxies. So remember from the previous animation, the further away a galaxy is, the faster it would seem to move. And this is precisely what you see in this plot here. This is from the original Hubble observation. So the further away, the faster the expansion. That means that you have to fit a straight line. That's precisely what Hubble has done. Fit a straight line through these data points, and the slope of that line is the expansion rate of the universe. And this parameter today, how fast is the universe expanding today, is called the Hubble constant, in honor of Edwin Hubble that first discovered it and measured it. Now, 90 years later, or probably 100 years later, almost, the measurement of the Hubble constant is a much more complicated business. And Hubble had at its disposal only a handful of galaxies, as you see in the previous plot. Here you see, as you've seen in the JWST image, we nowadays have plenty of galaxies, and this allows us to measure the Hubble constant to much higher precision. But as the saying goes, from great power comes great responsibilities. So to reach high precision, we actually need to take care of observational systematics to a much greater level of details. And in fact, the way in which the expansion rate of the universe is measured today, it involves not only one plot, as in the measurement from Hubble, but an entire ladder of cosmological distances. And I'll walk you briefly through this ladder in reverse order. So the first step of the ladder, we start with the last rung of the ladder, which involves supernovae, exploding stars, right? This is one of the key aspects, because as we've seen, to measure the Hubble constant, we need to estimate redshifts or recession velocities of the galaxies, and we need to measure their distance in a precise way. So the second part of the exercise, so measuring distance, is the most difficult one, and that's where supernovae are really the key to the success of this measurement. So the type of supernova that's being used is very special. It's called supernovae 1A. It's not just any type of supernovae, but it's one that arises from a binary system, and it's a binary system that has two stars, and one of them is an old white dwarf. Right? A white dwarf is a type of star that's formed after a normal star has exhausted its fuel has gone through a series of explosive phases that resulted in the shedding of its outer layers, and the core of the dying star is a collapsed state in a dense hot object that's about, for a normal object, it's about the size of the Earth, with a mass that's similar to the mass of the sun. And a white dwarf is white because it's extremely hot and dense. Now, in this, the white dwarf is not supported by any nuclear reaction. It's just supported by the fact that you can't compress matter any further, right? And in a binary system, you have a white dwarf that's accreting material from its companion. So, and at some point, it's going to accrete enough mass that can be converted into energy through an explosion, right? So, and this threshold mass is constant, only depends on the details of how electrons work. Basically, it's known as the Chandrasekhar mass. Now, when we have supernovae that are blowing off in this type of binary systems, it means they all have the same type of fuel reservoir to burn in an explosion, right? So since all supernovae type 1a have the same amount of fuel to burn, they are the perfect indicator of relative distance. And for this reason, they are called standard candles, right? So a standard candle is a source of light that always emits the same amount of light. Now, if we find such an object, we can measure very precisely relative distances. So, and this works really in the same way as with cars on highways at night, right? So if you imagine that the lights that a car would emit from the lights, if you assume that it's quite similar across different types of car, which is not totally true, but assume that that's the case, then if you see a dimmer light, it means that the star is actually further away. And the same goes with supernovae. Since supernovae type 1a always explode with the same energy reservoir, if we see a dimmer supernovae, it means it's further away. So that's the way in which we can measure relative distances. We can compare the luminosity of two different objects. We still need to calibrate their absolute luminosity to use it to calibrate distances. And that's where the lower distance ladder rungs come in place. And below you see, just below the supernovae step, you see a step that involves Cepheids type of stars. So Cepheids type of stars are variable stars that change their brightness over a regular and predictable period of time. And their brightness changes are caused by pulsation in the atmosphere, which causes their size and brightness to vary. And the idea is that the bigger the star, the brighter the star, the longer it takes for these pulsations to occur, right? Because you have, because colloquially you have to displace more material. And this is the core idea of the period luminosity relation for Cepheids. We can measure very well the period of fluctuations in the luminosity. That's literally comparing the same image of the same star across time. And we would see a source dimming and getting brighter on a period of days, as you see in this figure. So after we measure that, we can tell whether Cepheid stars are brighter. Brighter Cepheids would be further away. While with respect to, it's a little bit late, brighter Cepheids would be closer with respect to Cepheids that are further away, that would be dimmer, like, and with, with longer periods, once we take into account the periods, right? So this allows us to calibrate the supernovae, but we still need to calibrate, that's again a relative distance indicator, right? We still need to calibrate the Cepheids, which is done with the last rung of the distance ladder, which is comprised of objects that are so close that we can just directly measure their distance from us. And this is done through the methods of parallaxes that you are probably familiar with. And the idea is to measure the apparent position of a star relative to the background when the Earth is at different position in its orbits. And if you measure the apparent position, then it's just a matter of measuring the angles, and you would get and since we know the trajectory of the Earth, then you can calculate the distance to the stars or to the object based on this. And the overarching idea of the distance ladder is to connect all these pieces. We start by measuring distances with parallaxes, of objects or galaxies that have Cepheids inside them. Then we measure the luminosity of Cepheids in galaxies in which we see supernovae of type 1a, and then we use supernovae measurements and their redshift to measure the Hubble constant. And so once again, once we do all this and we tie all these pieces together, we finally get the measurement of the Hubble constant that we have locally, that we measure locally and close by in our universe. And that turns out to be about 63 kilometers per second per megaparsec. This means that if an object is at a megaparsec of distance from us, we would see it moving away from us at 73 kilometers per second, which is about 150,000 miles per hour, if you wanted to compare it with our daily commutes. So this is the measurement of the Hubble constant from local observations. Now, I want to briefly tell you how we measure the same quantity, how we calibrate the same measurement of the expansion rate of the universe, but in this case, this measurement is happening on the other hand of the universe, when the universe was young. So not at late times, but in the early universe. And you can immediately, as a consequence of the fact that the universe expands today, this means that in the past it was smaller. And since there's but basically by definition, nowhere to go outside the universe, if you compress the universe, without external exchanges, what happens is that, you compress things, pressure rises, and most importantly, temperature rises. And this is the reason why the early universe was hot, right? And it was so hot and dense that hydrogen atoms could not form. So an hydrogen atom is made of, it's the simplest atom we have, it's made up by an electron and a proton that are bound together by electromagnetic interactions. But in the early universe, thermal radiation was energetic enough that as soon as a hydrogen atom would form, then there would be some light going around that would break it immediately. But as soon as expansions of the universe progresses and the universe cools down, radiation now can't break apart hydrogen atoms anymore. And in this case, hydrogen atoms can form and radiation can freely travel throughout the universe. And radiation, this afterglow from this phase where the universe was hot and dense, is the cosmic microwave background, which we measure today in the microwaves, and that you see here. This thing that you see is the state-of-the-art picture of the early universe made by the Planck satellite about 4 years ago. This is a full sky map, so it's projected on an ellipse, as it happens with maps of the globe that we are used to see. And in the sky map, you can see different colors, right? And these were places where the universe was locally slightly hotter or slightly colder. Now, recall that in this case as well, slightly hotter means a little denser, right? But we know how gravity works, and if something is dense, it will, gravity will be locally will pull in things slightly more. So the temperature and density fluctuations we see in the microwave sky are the result of a complicated gravitational dance, right? On one hand, gravity would want to pull things together, make dense things denser. But if you start pushing a lot of hot gas together, pressure will locally increase, and this will balance gravity, that causing a backward expansion of the hot gas. So in the early universe, this gravitational compression and pressure release was continuously going on, giving rise to the patterns in the sky that you have just seen in the CMB map, right? So, and the physics of these fluctuations is exactly the same as the general physics of vibrations in a medium that you see portrayed here. Notice here the resemblance between the two pictures, and this arises because the two phenomena are fundamentally the same. In this video, in this music video here, you see a tiny pond of water on top of a loudspeaker that where music is injected. In our case, the driving force is gravity, and the vibrating medium is the entire universe. But it's basically the same thing, and it's the same. It's the patterns are fairly similar. Now, if you notice in the video, the pattern of vibration on the surface is regular at first, and then it becomes more complicated. And I removed the audio from the clip because I didn't want to overlap with it. But you can imagine that in the first case, the music playing is a simple pitch, while in the latter case, it's a more complex, organ sounding sound. Now, what we are seeing, what is happening is that vibrations of different frequencies are superimposing, right? So if we take a string, a drum, or some water on a loudspeaker, and we pluck it, the medium will vibrate at a number of frequencies. And in the most idealized case, these frequencies are all multiple of a fundamental frequency, right? All integer multiple of this fundamental frequency. And basically the fundamental frequency only depends on the propagation speed of the vibration on the medium and the length of the string that we are considering now. So if we take a musical instrument and we play a note, in this case from a piano, as you can see in the figure, and we look at its frequency content, we would see a series of peaks like in this picture. And as you can see here, we would have a first peak, the lowest frequency peak, which is the fundamental tone, and then higher harmonics. And as you can see in the figure, all the higher harmonics are evenly spaced between each other, since they're all multiple of the same base frequency, which defines the pitch. So the different heights of the peaks in the frequency content of an instrument define the sound quality of the instrument, and that's called the timbre of the instrument. And here you see two instruments playing the same pitch. On the left you have a piano, and on the right a guitar, and the note they're playing is exactly the same, but you can see that the frequency content of the two sounds is very different, and that's precisely how we can tell the two sounds apart, right? So let's get back to our picture of the universe, and let's look at its frequency content. Right, so now imagine that this is just vibration on a pond, and let's look at the frequency content of this image, and this is what you see here. Now on the horizontal axis, you have frequencies. These are slightly more complicated frequencies with respect to a musical instrument because this is all happening on the sphere, so it's vibrational modes of a sphere, but it's conceptually the same idea. So we have frequencies on these x-axis, and then on the y-axis we have power of vibrations or fluctuations at that given frequency. Now, just take a moment to appreciate how similar this is to the one that I showed you before, coming from musical instruments, right? So in particular, what you can see is peaks And the first peak corresponds to the fundamental vibrational mode, and it sets the pitch. And you can also see that the overtones are regularly spaced in frequency and multiple of the fundamental frequency. So as we have seen, the fundamental frequency depends on the length of the vibrating string. And in this case, it's exactly the same. The fundamental mode, the pitch, depends on the size of the universe at the epoch when the first hydrogen atoms formed. Now, thermodynamics tells us the redshift at which this happens. The spectrum of fluctuation tells us the size of the universe. So we have distance, we have redshift. So we can basically calculate the Hubble constant. And that's how it's done. Here are the two results. And as you can see, these two measurements are different. Now, in physics, you would normally expect different measurements to be different, right? That's because our measurement apparatuses are not perfect. And we always make some sort of, hopefully small errors, right? And this is what you see here quantified by the plus minus sign. That's the estimate of the error that we are making on these two measurements. And in this case, the error is low enough that the determinations of the Hubble constants with the two methods are precise enough that we can tell them apart from each other and say that this is a statistically significant discrepancy. They are different more than basically our noise estimates. But there is an important caveat, right? While the Hubble constant today is measured with nearby objects, it's really measured today. The Hubble constant that's measured through CMB observations is performed at the other end of the universe. To write the two quantities at the same time, to say the expansion rate of the universe today, we have to take the measurements from the CMB and extrapolate it, assuming a model. So that's why we are all excited about these discrepancies, because they might signal, a problem with the model that we use to extrapolate these measurements from the early universe to the late universe. Now, I want to tell you something about the second discrepancy, because to try, to tell you a coherent story of these two discrepancies that became significant in the last few years since we last talked. And the second discrepancy concerns the growth of structures in the universe. As you can see in this video made, from a giant computer simulation by the Illustris team. Now, as you can see in the simulation, what is happening is that initially density fluctuations that we have seen in the CMB will start growing under the influence of gravity, and eventually, you start clumping together enough mass that stars would start forming, and they would eventually start dying, exploding like supernovae. And in the simulation, you can see, that galaxies forming and supernovae blowing off gas, where we have more galaxies and we have regions where more stars are forming. Now, as you can see in the simulation, by gravitational pull, structures are actually growing in time. We see as the time in the simulation progresses, we see a sharper and sharper picture of what's called the cosmic web, right? Which is the structure along which galaxies would distribute due to their mutual gravitational pull. So now, as you can imagine, precisely in the same way as it happens for the Hubble constant, we can go back to the CMB. Now, we have seen that in the CMB, we measure the Hubble constant, but we have seen that different colors in the figure correspond to different regions that are overdense and underdense. These are the density fluctuations that when pressure support ends, would eventually grow So this is why the CMB is so important when we study the distribution of galaxies as well. It provides the initial conditions for cosmic structures to grow. Cosmic structures will grow out of the inhomogeneities that we see in the CMB. So when we compare this picture of the CMB with the distribution of galaxies, we are looking at the same system about 14 billion years later. So I want to briefly tell you how we measure cosmic structures in the late universe, because that's something that I've been spending a lot of time in the past couple of years working within the dark energy survey. Now, differently with respect to the CMB, in this case, we have to map the distribution of galaxies in the universe. This means measuring the positions and distances of many, many galaxies. And so that we can use these galaxies as dust on a pond to tell what's the underlying distribution of matter in the universe. So as you can probably imagine, since we want to measure many, many galaxies, we need giant telescopes. That you see in the video, you see the dome of the telescope that hosts the Dark Energy Survey. And so I want to tell you a couple of facts about the Dark Energy Survey because it's pretty fun. The telescope is located on top of Cerro Tololo in a remote part of Chile. And it's fairly big by telescope standards. The assembly of the telescope finished in the 1970s. And when completed, it was the third largest telescope in the world. The main mirror is 4 meters wide. And these structures are so big that their weight would deform them and it needs to be balanced, right? So the assembly uses a design that's called a Serrier truss, which is made to balance the effect of gravity on the telescope itself. So that's why it looks so complicated. And in the 70s, all bigger telescopes were built in this way. I think at least the top 3s were. By today's standards, the telescope is not particularly big, though. You can compare it with JWST in space. That's that lens, JWST lens at 6-meter aperture, right? So it's bigger than the telescope that's used for DES and in space. But but this is ideal for the task that we have at hand. So while JWST is trying to measure the details of the single object over a very tiny field, the purpose of the Dark Energy Survey is to measure a lot of galaxies. So that's why we are not really interested in measuring all the details of a single object, but just a large number of galaxies to use them to trace the overall matter distribution in the universe. So the Dark Energy Survey mounts a giant camera, which is about 500 megapixels that you see on the left in this slide, which is mounted on the telescope, and it images a large swath of the sky. And on the right hand side of the slide, you can see a rather cleaned exposure of the camera, and unfortunately you can't really tell where all the segments, where you have those tiny holes between the segments, that would basically mirror the disposition of the assembly of the camera. And as you can see, each exposure gives you a large area of the sky and a lot of galaxies. And in this way, the Dark Energy Survey measured across 6 years of data taking the position, distances, and shapes of about 400 million galaxies, which feels like a large number. And in particular, the main goal of the survey was to measure the shape of galaxies. And the reason why, the reason for this design choice is that the distortion of the shape of a galaxy carries key information about our universe. And in fact, as light from a galaxy travels towards us, it encounters a massive object like a galaxy class, a cluster of galaxies, many galaxies clamped up together. The path of light would be bent in a phenomenon that's called gravitational lensing. But these giant cosmic lenses are not perfect. They're not meant to give us a good image, right? Unlike our glasses. So they distort the shape of the galaxy that is passing through. And here you see an animation of this effect. This is a simulated effect, but you can see that, by the distortion of many galaxies, by combining the deformation of the shape of many galaxies, we can tell something about how much mass is in the lens and basically how thick the lens is. So you see in this video simulation of this effect, you see a mass that's swiping through a field of galaxies, and you see the deformation of these shapes. So what the dark energy survey was set up to do was to get the distribution of mass in the universe through this effect using hundreds of millions of galaxy shapes. So here you see the results from 3 years of observations, the results with 6 years of observation. So the full survey results are still being worked on and not public yet. So we are working on these days, basically. So in this map here, you can see stars for, in illustrative purposes on a very clear night sky. A very clear night sky from the Gaia satellite. So it's as clear as it gets. And in purple, you can see the distribution of dark matter mass, of mass in the universe over a large swath of the sky. And the shape of the survey in the sky is fairly weird. It kind of looks like a tank, but it was meant to maximize the overlap with other smaller surveys and allow for the comparison of results, in subset of the sky. So each of the area was built to overlap with something else, and then the very large area was just meant to cover a lot of sky. And the map you see here in this figure is the largest map of the distribution of cosmic structures available today. Now, when we look at this map, one of the things that we can measure from it is how clumpy the universe is. You see here 3 simulations again, because we use a lot of simulations because that's where we can control the parameters of the simulations. You see 3 simulations, and in each of the simulations, I have dialed the parameter describing how clumpy the universe is. This parameter is called S8 for historic reasons. And you see here what happens when it takes 3 different values, from more clumpy, higher contrast, basically a higher contrast universe, to less clumpy on the right. And the idea is that we can measure this clumpiness in the initial conditions in the CMB. So we can measure how clumpy the CMB looks like, and we can measure how clumpy galaxy look when we reconstruct them with galaxy surveys at late times. So again, at the other end of the universe. And again, these 2 results are different. And as you can see here, as in the CMB case, in the top line, the CMB measures a universe that's more clumpy than what we see with galaxies, compared to the second line, where you have the direct measurement from the dark energy survey. And again, you can see that these 2 measurements are at about the same level of precision, and they differ by some quantity that's statistically significant. And you see here in this figure both results at the same time. You have the two direct measurements from the two direct observables, right? The expansion of the universe through, local measurement of the Hubble constant, the growth of cosmic structure or the clumpiness of the universe from measurements of the dark energy survey, all in black, the two vertical and horizontal bands. And in red, you see measurements of the CMB in the early universe extrapolated to the late universe. Now, I've highlighted how different these two are in language that's really used by physicists, by 5 sigma. If you've ever encountered this type of lingo, for example, in particle physics. 5 sigma is a distance from which you can tell these two things apart enough that, in other fields of science, in particle physics, would be enough to claim the discovery of a new particle. And, in other fields of science, a result that's 3 sigma, or, it's 99.7% significant, that's the discovery of the cure for a disease, right? So both these discrepancies are nowadays statistically significant. And if we could explain those, we have enough data power to claim the discovery of some new physics that would explain them, right? And the fact that these are 2 means that we can, we can use one to confirm the other, right? You could play the game where you try to explain one of these 2 tensions and predict the solution to the other. Now, what could be the explanation of these 2 tensions? That's, as you can imagine, a large swath of the community is working relentlessly, either to find systematic effects in the data or to find a physical model for these discrepancies. And, it's not like we lack possibilities. I'll circle back to the picture of the standard cosmological model. Most of the things in the standard cosmological model are of a known physical origin, right? Dark matter and dark energy, they make up most of the budget of the universe. They are relevant at late times with respect to early times. And, it could be that we could be seeing the properties of these dark components of the universe. Now, if we circle back to these discrepancies, you can see that these are discrepancies at about the 10% level. These are discrepancies of order 10% of what we are measuring. Dark energy is a 70% thing in the universe, which means that we're not really discussing the existence of dark energy on its own. What we're looking for is the properties of dark energy, right? You imagine that, you have an unknown in the universe, and we are kind of trying to zoom in on its properties. Now, the part of the message I want to leave you with tonight is that there's no known solution. So there have been many attempts in the community in many different directions, but still there is no known physical model that would manage to solve both tensions at the same time. And here I've basically listed all the things that I've tried, collaborators and colleagues have tried. And if you're interested in some of these, I can go in some detail about this later. But basically some of the ideas go as of adding some sort of new dark energy modification in the early universe, or, for example, add neutrino species. We know that in nature we have 3 neutrinos, but we could have 4. And this could go in the direction of alleviating the tensions, but it really can't solve both tensions at the same time. Or people have thought about different or additional interactions to the standard model, or between standard model particle, or between standard model particles and dark components, or neutrino masses, or neutrino interactions with other components of the standard model. Or, since this is a discrepancy between the early times universe and the late universe, we could think of modifying either the early universe or the late universe. And in the late universe, we have plenty of possibilities playing with exotic dark energy properties or exotic dark matter properties. Different theories of gravitations, interactions between dark energy and dark matter, or playing with the geometry of the universe. The bottom line is that none of the things I've listed here forms a complete coherent history. And the solution to this tension puzzle is to this day unknown. So I want to close on a summary of and road aheads, a brief summary of what I told you. So I hope I have convinced you that our understanding of the universe today is challenged empirically, right? We measure the expansion rate of the universe at late times and in the early universe. And from the early universe, we extrapolate the results to late times and we compare the two, and we find a statistically significant difference between the two at the level that in particle physics would allow you to claim the discovery of a new particle. And then we measure the growth of cosmic structures, giant structures of galaxies in the universe that form, from initial conditions in the early universe, out of initial conditions in the early universe, and grow. And we basically compare these two pictures of structures in the universe. And again, we find that the results of these two types of measurements disagree to the level that in other fields of science would be enough to claim a discovery of a new medicine. And any physical explanation will require a radical rethinking of the models that we have of our universe. And one of the challenges that we're facing today is that none of the explanations that we could come up with immediately in the last couple of years basically would work at explaining in a coherent picture all these observations and building a coherent story of the early and late time universe. So with this, I thank you. I've basically timed to end on like 50 minutes mark. So we can have some sort of discussion now, and especially if you want me to go through some of the details of the models that have been studied to address these type of tensions, I can elaborate a little bit more. I didn't go into much details because fundamentally none of them really works. So it's that there's a fine line between, spending a lot of time to describe something that eventually doesn't really do the job. But I'll be happy to discuss them. Thank you.
Marco, question.
Sure,
Let
please.
me ask you a silly question. When you refer to exotic, when you use the term exotic to describe dark energy or dark matter properties or even gravity, what does that mean? Something like from a quantum mechanical or quantum physical way, or what is that term meaning that you're invoking?
Yeah. So it means that a large swath of the community used a lot of fantasy to produce these models. So the quantum question is very interesting. So exotic doesn't really mean from a quantum perspective, because these are all very macroscopic objects, right? So you never probe the microphysical object, but you only see the very large scale properties. So pressure in a fluid is eventually electromagnetic repulsion between things, or interactions between particles, but at the macroscopic level you see it as pressure. That's basically what's happening in these models. So when we talk about exotic dark matter properties, dark matter is thought to not have any pressure, for example, right? To only interact gravitationally with other things. So you could start saying, okay, what happens if dark matter does have pressure, right? And pressure would the idea is that pressure would decrease the growth of structures because clearly, gravity wants to pull things together. If you balance with some form of pressure, you decrease, you form less structures, which is basically what the data wants, right? But that's basically a macro physical description of dark matter. So, and it could implement it microphysically in many different ways, right? And but effectively you just see an effective pressure contribution or something like this. The same goes for dark energy. You could have, different types of microphysical models resulting effectively in the same macrophysical behavior of having, for example, pressure or a time evolution of density, which is different from the usual. And by exotic, I mean dark energy, for example, when it comes to density, the following happens. In the standard cosmological model, dark energy density never changes with time, right? Because in the standard cosmological model, dark energy is associated to the energy of vacuum. Now, if you have an empty box and you say that the box has some energy content, if the box becomes bigger, it's still empty. So it still has the same energy density that it had before. So that's the property of standard dark energy, or dark energy as it enters in the standard cosmological model. It's basically defined as something that won't change density as you expand the universe or as you expand the box. But you can obviously play with these types of models and say, okay, what is happening if dark energy density now evolves with time, as it would happen in different types of models, or for example, as it happened in the very primordial universe. So these are a couple of ideas. For example, when it comes to the gravitation, there you have a nice overlap with direct observation of gravitational waves, because you could say, instead of just having gravitational waves, you have an additional gravitational force, or you flip the sign of the gravitational interaction. You effectively flip the sign of the gravitational interaction once you go to very large scales. So these are a little bit the ideas that then people implement and test against the data. And all these models would do some aspects of these tensions when taken singularly. So as I was telling you, dark matter with pressure support will counter-react structure growing and will help solving the growth of structures problem, but it won't really help with the Hubble constant tension, right? So it won't give you a coherent story. So I let me know if you want me to talk a little bit with more detail on some of these.
Does antimatter factor in at all?
Not really, right? Because when antimatter meets matter, which would happen, right? So imagine. So I want to show you back, the simulation of the growth of cosmic structure. That's pretty messy. I hope that the video delivers the message, right? That you have a lot of stuff that's smashing into each other, right? Now, if you had antimatter staying around, what would happen is that, once it's all mixed up, it will meet matter and it will annihilate, right? Emitting light, right? So that's very violent, and we would basically see it with telescopes, right? So that's actually one of the mysteries in the standard cosmological model that are largely unexplained by it. Where is antimatter? There's nothing that really discriminates matter and antimatter in the in the standard model of particle physics, right? So you could think that in the primordial universe, whatever was working was making both matter and antimatter. But we don't see, if you have a galaxy made of antimatter and a galaxy made of matter, and you have them collide, that's a very big flash of light, okay? Because it will immediately entirely annihilate, right? And we just don't see that. So one of the mysteries is, where is antimatter? So what is thought is that in the primordial universe, there's some phenomenon in a very high energy particle physics phenomenon, which does prefer matter versus antimatter, and then ends up producing more matter with respect to antimatter in the primordial universe. And then basically, you don't have these problems with, galaxies disappearing when they meet in a giant flash of light. So I hope this answered your question a little bit.
Thank you.
Mark, I'm going to ask you a question. It's more maybe a philosophical one. So, given all the advancements that have been made since Hubble first, proposed the expansion of the universe, and all the instrumentation and the precision in which we can do things, the fact that there's no clear, cogent solutions or resolutions to these discrepancies, do people in the cosmology community think, oh, well, that's just the way it is? Or is there some optimism that, breakthroughs are just, on the horizon, that based on what we know or what we're starting to know, in 10 years or 20 years, we'll understand it? Or are people just saying, well, we may never understand this and we just plug along? You know what I mean? It's like hopeful versus existential. I don't know how to put it, but
So people are really excited about these, because potentially, if we had a good idea, we could know tomorrow. That's the point, right? So I was trying to highlight the statistical significance of these tensions, because if you can explain them, you have enough data power to claim a discovery. So part of the physics community is limited by having a good idea, which you can try. That's why people are really excited, right? If you come up with a good idea for a model that solves these tensions, then data power is not a problem. If it's solving them, you'll have enough data power to claim a discovery. So I think that's the first time it's probably not the first time that this is happening, that you see a discrepancy in the measurements and it's statistically significant enough that then whatever will come next will explain that, and it will all seem natural, right? Something similar probably happened with, the precession of Mercury. That was a known anomaly, the fact that the orbit of Mercury would proceed faster than expected in Newtonian gravity at the time, right, was a known anomaly. It was detected to have, high statistical significance. And, nowadays we know, of course, it's general relativity. That's an effect of general relativity, right? And really only what it took Einstein was to come up with a model, fit existing data, and then basically everything took off from there. I mean, it still took some years, of course, to be accepted by the community, but Einstein had all the ingredients for a discovery in his hand, right? So somehow we are nowadays limited by our theoretical fantasy, which feels, at least it feels cheaper than big telescopes, I would say. So that's where community where the community stands. Now, there's always the possibility that this is unforeseen systematic effects, which is obviously the case, right? As you were saying, instruments have become significantly more complicated, right? And the precision has increased, so perhaps we are missing something somewhere, and it's not really a glamorous discovery. It's just some problem with the data analysis pipelines. But to this end, what's comforting is that, you know, at least one of these two discrepancies is long-lived. So the Hubble constant tension is basically around since 8 years, perhaps, and it only recently became highly statistically significant. But, you know, before it was somewhat statistically significant. While the growth of structure tension also was around for quite some time, and just now starts becoming, you know, starts growing into the more significant territory. But it still kind of have to transition into the 5 sigma territory, which is, you know, super large statistical significance. So on one hand, we will have a new generation of data taken from ground-based, space-based facilities, which will be doing for example, the same exercise of the dark energy survey, but from space on the entire sky. So those will hopefully transition the structure growth tension into, you know, this higher statistically significant regime, right? Or explain if it's a systematics as well. So that's a little bit the hope. But if it really is physics, then we already have all the ingredients, and we just need good ideas. That's.
Thank you. Any other questions for Marco? Marco, thank you so much. Again, really appreciate not only the talk, but the time differential. So thank you again.
It's really a pleasure. Okay. Yeah, it was really a pleasure seeing you all. Yeah, thank you for inviting me. Yeah.
Get some rest.
I will surely do. I will surely do now. It was really nice seeing you. I'll see you next time.
Thank you. Thank you.
Bye. Bye.